Okay, next topic is forecasting. This is second last topic in F2. Forecasting and budgeting and standard is usually used together in a question because they are related. Forecasted figure or budgeted figure or standard figures, they have relation. I already explained what standard and budget means. So forecasting involves predicting the future outcome, mostly using the data in the past. And once we predict the outcome, we make a standard and budget from that. So forecasting and standard and budgeting is kind of related. Okay, so forecasting involves everything about the future, mostly using past data. One thing we look at, the first thing we will look at in this chapter is relation, correlation. So whenever we want to predict outcome, mostly sales units, cost, anything that we want to predict, we want to see its relation with something. That is called correlation. For example, if you want to know whether the sales of ice cream, let's say it is a product that you are selling, has relation with temperature or not, that is called correlation. So to find the correlation, we find something called correlation coefficient. We will see that in a minute, but once we try to find correlation between two figures, and it will be two things, not more than two. So more than two is out of your course in F2 level. So if you want to know the relation between two or more variables, we look at that in correlation. Correlation could be positive or it could be negative. So this is the first thing we need to understand. Something could have a positive correlation, which means when it increases, another thing increases with it. So let's say we want to know the relationship between advertisement and sales. When advertisement usually increase, sales will increase with it. So there is a positive correlation. So when one thing increases, another thing increases with it, we have a positive correlation. A negative correlation is when one thing increases, another thing decreases. For example, sales price and demand. Usually, when we increase sales price, demand for the product decreases. I'm talking about usually, okay? Sometimes it happens when we increase price, demand increases, but that is other thing. I don't want to go into details into that. That actually I have already covered in pricing chapter in F5. So normally when we increase price, demand will decrease. So it has a negative correlation. And correlation, we will see when we look at the formula, will have a value from positive 1 to negative 1. So if it is exact 1, it means it has a positive correlation. If it is exact negative 1, it means it has a negative correlation. If it is exact 1, it means it is a perfect relation. A perfect relation means that the relationship is 100% dependent on the dependent variable. For example, if I say the correlation between price and demand is 1, then it means is that 100% of the change in demand happens because of the change in price. There's something else as well, correlation of determination. I will leave that on the side for now. But the closer the value is to 1, the stronger the relation is, and the easier we will be able to predict it. The far the value is from 1, the difficult it is going to be to predict, because if there is no correlation or a weak correlation, then it would be difficult to predict. Value will not be more than 1, it will not be less than -1. So we could have other situations as well where we have, so in the first one that I explained, the perfect correlation is where all the data, if we want to draw a line of best fit, all of that data will come on that line. If it is a negative correlation, then all of the data still comes on the line. So remember, we usually put the dependent variable here and the independent variable here. Dependent and independent variable I already explained previously in other chapters, but I will explain it here as well. Dependent variable is something in which change is cost. An independent variable is something that causes change. For example, if we look at units and cost, there is relation between units and cost. The more units, the more will be the cost. So in units and cost, units is the independent variable because it causes the change, which is the cost. So with units, cost will change. So we say the more the units, the more will be the cost. We don't say the more the cost, the more will be units. It doesn't seem right. So we usually put, in our example, cost on y-axis and units on x-axis. So the more units, the more the cost. In the example of the discount price, the demand would be y-axis and the price would be x-axis. Now I'm not saying units will always be the independent variable. Like in price and units, the units becomes dependent variable. So we could have a strong relation, or we could have a partial relation where it is moving in a direction but not exactly in a straight line. Some data is above, some data is below line. We can still draw a line. We still know there is a direction, but it is not exactly straight. Or we could have another example where there is no relation. You could draw a line here if you want. You can draw a line here if you want. So it means there is no correlation. So correlation could be perfect, which means exact one. It could be strong, which means near one, not exactly one, but near one, maybe 90%, something there, 0.90. And it could be partial, which would be 50% and above. If it is less than 50%, 0.50, then it means it is a lower correlation, not very strong. So we find correlation between two variables using a formula. And this formula is going to be given to you in exam. So I'll go to Excel sheet. This is the formula that is used to find relation between two variables, and it is represented by R. So let me explain the formula. You don't have to memorize it. You just have to know how to put the figures in formula. That's it. So we have n number of data. This sign represents sum, and then x is units, x is the independent variable, and y is the dependent variable. Minus sum of x, dependent variable, multiplied by sum of y. And then divide that by square root of number of data, sum of x squared minus sum of x squared, and that whole thing multiplied by n sum of y squared minus n sum of y squared. So what you need is about 6 things. You need x, you need y, you need x into y, you need x squared, and you need y squared. I have an example here, and I will show you how data is found and how it is put in calculator. So using data below for variable x and output and y total cost, calculate an equation to determine the expected level of cost for any given output using the least square method. So the first thing obviously is you need to identify what is the dependent variable and what is the independent variable. Obviously in output and cost, the output would be independent variable and cost would be dependent variable. So we have period, which is pair of data, 5 pair of data. When units is 20,000, cost is 82. When units is 16, cost is 70. So we want to see how strong the relation is, and that relation is found using R, and R is found using this formula. Okay, so the first thing I've done is copied what is given here. So n pair of data is 5 pairs of data. I've written units here, I've written cost here. So the first thing I will do is sum this. So this becomes sum of x. And then sum this one. This becomes sum of y. Next thing I need to do is take x, multiply by y. And then I will do it for all. And then when I sum it, it becomes sum of x into y. And then I will take square of x for all, and then I add it, becomes sum of x squared. And then I do this for y as well. So these are given in formula, you know what things you need. So add it together. So now we have all the ingredients for the formula. We have sum of x, sum of y, sum of xy, sum of x squared, and sum of y squared. Obviously, if you put this whole thing in calculator, it will be a little bit difficult. So my recommendation is do it in parts. First thing, find the figure at the top, which is n, which is 5, sum of x, y, which is this one, it is multiplied. I'll put it in brackets, and then minus. So how do you know whether you have put this figure right in the exam? This will either give you a right answer or completely wrong. So if your figure is different than -1 and +1, then you know it is wrong. Either it gives you exact right answer or it gives you wrong answer. So that way you know whether you have calculated it right or wrong. So we have sum of x into sum of y. So we have 100 multiplied by 400. So I will leave that there. And then I will do these. Maybe you can do these two in 2 parts as well. But we are basically taking number of x squared, then minusing this part, and then you're doing the same for y. So we have 5 multiplied by x squared, which is 2040, minus x squared, which is 100 power 2. and then I will multiply that with 5, doing the same thing for y. 400 minus, remember here this is outside the bracket, okay, this power. So sorry, this is 3278 minus y 400 power 2. So if you're scared, you can put brackets here as well. So as I said, it will either give you exact answer or it will not give you exact answer. So what I will do, take my calculator and find square root of that. So if you put it in your calculators, 278,000 gives you 527. So the result of this is 527. So I'll write this here, 520 divided by 527, and take one divided by the other. We have 0.98. So it is right. I would know exactly when the answer is wrong because it would be completely wrong. So the answer range should be from +1 to -1. So this is relation. So there is a relation between units and cost, and the relation is not perfect. If it was perfect, it would be 1, but it is strong. Anything near 90% would be strong. We have something else as well, correlation of determination. If I take this R and I square it, it gives me correlation of determination. Now this 97% means 97% change in cost is caused by units. Remaining 3% is caused by other non-explained things here. So R shows you the relation, and correlation of determination, which is R squared, gives you the percentage change caused in Y by the percentage by the change in units in X. We looked at that at this in the statistics chapter as well. Okay, so this formula shows R. Now this topic will come for 2 marks, so I would not expect you to do all of these things. So usually maybe these figures are given and then you have to put it in formula, or maybe they ask for a specific bit here. We will look at that in kit questions as well. The important thing, the challenging thing, is how you put the figures in formula. Okay, so using this correlation coefficient, we can find this shows us relation. We have another formula very similar to this, which will show us output, like we saw in cost behavior chapter, high-low method. When units were given, we found total cost. So what we did is we found the fixed cost and the variable cost, and then using that we calculated total cost. The same thing if we do using high-low method. Let's say if we want to see the variable cost and the fixed cost in this one, using high-low method, high activity is 24. Remember, you decide using activity, not using cost. So we have high activity and low activity. High activity is cost and low activity is cost. So we have the variable cost, which is the cost of the high activity, which is 90, minus the cost of low activity, which is 70, divided by high activity minus low activity. $2.4 is the variable cost. So if you want to find fixed cost, take any activity. Let's take high activity's cost, minus variable cost into units, which is 24, which gives us 30 fixed. Now this is a good method, simple method, but the thing about this is it only looks at the high activity and low activity. It doesn't look at anything in between. So if low activity is low activity's cost is, let's say, unreasonably lower or maybe higher, or high activity's cost is unreasonably lower or higher, then it doesn't represent the overall data. So then we have another method which looks at the whole data. So it uses the same principle here. The data that we use for it is the same data here. So we have the same principle, which is total cost equals A plus B into units. For example, if you want to find the cost of, let's say, 30 units using, I already said, let's say 22 units, then we take the variable cost plus, fixed cost plus variable cost into units. That will give us total cost, which will be 85,000. So we will find B, which is the variable bit, which is also called gradient of the line. So what this actually does is it shows us this slope of the line. This is called gradient of the line. Sometimes in questions it is told that the slope of the line is something like that. They don't tell you that it is B. So you need to understand that B means gradient of the line, or the slope of the line. And then A would represent that fixed element. So let's go back. So we have all the ingredients that we need. This formula is also given to you. So let's find the B first. If you see the top of this formula and the top of this formula is similar, so I can just copy this. And then the bottom is also similar, only we are taking only this part. So I'm going to take this part. So the step you take for correlation coefficient, you will need it here as well. So take one, divide by the other, gives you gradient of the line, that variable cost. Remember, it doesn't always have to be variable cost, because we are not always looking at units and cost. So if you see, it is very similar to this, but this is more accurate because it looks at all the data. Now let's look at the fixed element, which is sum of y, which is 400, divided by units, number of data, pair of data, which is 5, minus B. You can find A without finding B, just like you can find fixed cost without finding variable cost there. So 2.60 multiplied by sum of x divided by pair of data. So either it gives me right answer or wrong answer. So I have a fixed element, which is 28. So here you see variable was shown higher, lower. Here it is shown higher. Fixed was higher, and here fixed is lower. But we know this is more accurate. So now if you want to know the total cost, same formula will be used: fixed plus variable into units, which is 85.20. Not big difference, but we know the least square method represents all data, and it is more accurate than Harlow method. Okay. So this is one thing we use to predict future outcome. Next thing we look at is time series. Remember, we will do practice on it in KIT questions, So now I will explain the topics, and then for practice we will look at questions. Or what you could do is, if you watch video up to this part, you can go to the kids video and then look at questions relating to this part. You can do it like that as well. Okay, next we have time series. So this is the data that I already did in Excel. I've copied it here as well. So in correlation coefficient, we are looking at relation of x with y, x being the independent variable, y being dependent variable. And x can be anything, y can be anything. In time series, we are looking at relation of x and y, but x is always going to be time. We are looking at relation of things with time. And remember, time is independent because it doesn't change with other things. It causes change in other things. So time series analysis is when we look at the data over a period of time. Obviously in the past, and then using that, we can predict the future. A simplest thing would be, let's say we have a pair of data over certain years. We have pairs, we can draw a line, and then using that line, we would know where the data is going to be in the future. And we are not 100% going to be right, but that is the thing about forecasting. It is doing something. So it is good to be right up to some extent and then not to be right at all. So the things we look at in time series analysis is the trend. Trend is the direction in which things are going. It could be either increasing, like in this case, or it could be decreasing. Next thing is seasonal variation. A business could be increasing overall, but in some seasons, sales would be lower. In some seasons, sales will be higher. For example, ice cream in summer sales will be higher, in winter it is going to be lower. Jackets in summer is going to be lower, in winter is going to be higher. And then we have cyclical variation. Cyclical variation are caused by economic factors. So seasonal variations are short-term. They are caused by seasons in a year. Cyclical variation are a little bit longer term. It is maybe 5 years or 10 years. Every once in a while, because of economic factors, businesses overall becomes good or bad. And then we have other residual random things, like most recently Corona happened and it affected many business. It affected many business negatively, and it affected many business positively as well. We will not be looking at random residual variation or cyclical variation in questions. We'll only be looking at trend and seasonal variation here in F2. Okay, we have a question in Excel. Let's look at it and answer it using time series. Okay, so let's say we have data. Calculate moving average trend line of the following results of Linden Limited. So we have data given for 3 years, and then data is divided in given per quarter. So we have about 12 quarters. So what I've done is I've put this data here. So the first thing we do in time series analysis is find an average. So because it is quarter, we will find average of 4. If it was data for 6 months, then average would be for 2 pairs of data. So 4 pair of data here would give me average. So I'm adding 4 quarters. And then dividing by 4. You can do something called moving total as well. I believe they said here as well, moving average. Okay, they didn't ask for moving average. So moving total will be before dividing it by 4. So this is moving total. If they ask for moving total, this is moving total. But you can completely skip that point. So this is average. Now it is called moving because what we do is we add 1 from the bottom and remove 1 from the top. So I'm going to take this formula and paste it here. So it is automatically going to minus 1 from the top and add another at the bottom. So now if you see, it doesn't relate to any quarter because it is even number and there isn't any data in the middle. So next thing we do is we take 2 quarters, average, and then divide it by 2. That gives us a centered moving average because now it relates to quarter. Yeah, this should be my last figure because I don't have anything other. Now, if you look at this data, so it is not very clear that whether sales are increasing over time or whether they're decreasing. Sometimes it is higher, sometimes it is lower. Now, using this center moving average, we know that they are increasing. So the trend is increasing. But we want to know how much is it increasing. So we take the last data that we have, average, and the earliest data, obviously for the average. And we see how much period. So I'm counting the change. So in 1 quarter change, don't count the quarters, count the jumps. So 1 quarter, 2 from the previous one. So 2, 3, 4, 5, 6, 7. In 7 quarters change, we have total change, total increase of 37.5. And if we look at the quarters, in total quarters that it happens, 7 quarters. So we have 5.3 increase on average every quarter. So this is that line. So if you don't do it numerically, then visually, if you draw a line, that line would give you the same thing. Now, this gives us this line, but we don't know whether it is going to be, so the data is obviously going to be above the line or below the line. Line is this center thing. So we want to know exactly where it is going to be. Obviously, there's no exact in forecasting, but if we want to know up to more accuracy whether it is going to be here or whether it is going to be here, then we need to add seasonal variation. There are 2 methods of doing it. One method is additive model, another method is multiplicative model. So the data that we have done up to this point, I'll bring it here. Now, what we do in additive model, we look at the change in the seasonal variation. So if you look at the average line and the sales line, we know that there is negative 230 because it is lower. So seasonal variation in quarter 3 is negative. In quarter 4 it increases. Quarter 1 decrease, lower than line. Quarter 2 above the line. Quarter 3. So one quarter is higher, one quarter is lower. So this data is for individual quarters. So what we do next is take the years and put the quarters here. Take the earliest data that we have. The earliest data we have for seasonal variation is quarter 3. So I'm going to write that here, minus 0.30, and then following it. If we have full seasonal variation for quarter 1 to 4 from here for 2006. We don't have any other data. So now what we are going to do is add it. And because the pair of data is 2, I'm going to divide it by 2. It gives me this average seasonal variation. And we will do this for the rest. This data is also 2. If the data is 3, divided by 3. If it is 4, divided by 4. So it will give you that average. So this is 2 as well. This is 2 as well. So now these are seasonal variation. Now if I want to predict what will happen in a year, in a future, in a specific quarter, I can predict it. Let's assume what will happen in quarter 3 of 2010. So first thing we need to do is what is our earliest data that we have available. If you see the earliest average that we have available is quarter 2 for 2007. So we will start from quarter 3. So we have quarter 3 for 2007, quarter 4, and then quarter 1, 2008. So if you count up to this point, we have 13 quarters. So the average that we have in quarter 3 from the data is 687.5, and every quarter data increases by 5.35, and we have 13 quarters increase. So this will be that increase, and this would be where the line is going to be, that average line. Because seasonal variation in quarter 3 is going to be minus, that means that the data is going to be lower than the average. So we estimate that in quarter 3 of 2010, we will have 517. This is called additive model because we are using plus and minus. We can do the same thing using multiplicative model. I've already copied it. So in multiplicative model, rather than minusing or plusing, we divide. So if Actual data is more than the problem is you might forget whether divide this by this or this by this, or whether minus this from this or this one from this one. So remember, if in multiplicative model, if average is lower, higher, then seasonal variation should be negative. Season would be lower, the line would be lower, so it should be minus. So that way you would know. And here it should be lower than 1. 1 would mean, according to the average, more than 1 would mean more than average. Lower than 1 would mean less than average. So that way you know what to divide by what. So we will do the same process here. We have the data earliest for quarter 3. So we are going to do the same thing. So in fact, I can just copy this because we have the exact same pair of data. So if we want to predict the exact same data, then this figure up to this point, we do exact same thing. Let's multiply this by the trend. So up to this point, using multiplicative model or additive model, you will have the same result. Now we take a seasonal variation. We believe it is going to be 736. I believe I have made a mistake here. One, two, it's quarter 1. This is quarter 2, and then quarter 3, quarter 4, and I haven't found this one. Quarter 4 and then quarter 1. Quarter 2. Yeah. So we believe that the data is going to be 482, which is lower than what the multiplicative model shows us. Multiplicative model is superior because it shows a percentage. If you look at the trend, as a percentage, you can see the data, it is very similar. If you look at the actual figure, there is a big difference, especially in this one and in this one. So multiplicative model is superior because as a percentage, when sales increase overall, seasonal variation will increase and decrease as well. But as a percentage, they will remain the same. Okay, so this is done as well. Next, we look at index numbers. Index numbers is when we look at the change in price and the change in quantity over time, over the quantity that is sold for a certain product and the price at which a product is sold. So the quantity one is called price index, and the price one is called price index, and the quantity one is called quantity index. We have other indexes as well, but for now, let's look at price index. We have a question here. Price of commodity was 2.7 in 2010, 3.11 in 2011, 3.5 42 in 2012, 3.83 in 2013. Construct both chain-based index and fixed-based index for years 2010 to 2013 using 2010 as base year. Obviously, price is given here, so price index is formed. So you can find the index for the first year. We can't find index for the first year, which is 2010, because we have to compare it with something. So the first index we will calculate is for 2013. So in fixed base, what you do is you take the next year divided by 2.7 the previous year, and then you multiply by 100. We have 115, and it is not shown as a percentage. You just say 115. The price index for a certain product is 115. People will understand what it means. So we take 3.42 divided by 2.70. This is called fixed base because we don't change the base year. The base year is the same 2010. So this is for 2011. This is for 2012. And 13. Okay, this is fixed base because base is fixed. In chain base index, the first one would be the same. Now in the next year, we take the previous year as the base for next year. So it is like a chain. Now in fixed base, it always seems that it is increasing, but in chain base index, we can see that in year 2 that increase has slowed down a bit. So let's look at quantity index now. Number of units of coffee sold in 2010 was 500, in 11 700, and 2012 600. So starting with 2011, $140. So it is not shown as a percentage. It is shown in hundreds, and people understand what it means. And then in chain based, we take the previous year as base for this year. So you can see in chain base it is lower than 100%, but in fixed base it is still higher than 100%. So chain price based index looks at price change, quantity index looks at quantity change, and fixed base uses the original year as a base, and chain base looks at the previous year as base. Next we have composite price index, in which we look at not the price of one item, but more than one. Or if it is quantity, then we are looking at the quantities of not just one item, but more than one. So in this composite index that is given here, 20 cents, 25 cents, for 50 cents, we have total bread, tea, caviar together like a package. 40, 30, 405, we have 475. So 495, 475 divided by 495, we have 95. So overall, price has decreased. If you see, the price of bread has increased, the price of tea has increased, but the price of caviar has decreased. So overall, for all these packages, the price has decreased. But there is a problem in this one. The problem is that even though the price of packet of tea it has increased, but tea is usually used less in breakfast, or maybe caviar is used less as well, and the loaf of bread which is increased, maybe that is used more. So it doesn't look at the quantity that is consumed. That is why we have next indexes. We have Pache index and Laspe index. In Pache index, we look at the change in price. In price index, we look at the change in price. In quantity index, we look at the change in quantity. But in Laspe and Pache index, we look at the change in price, but we look at it in terms of the quantity consumed as well. In Pache index, we look at the change in price. We look at it in terms of the change in quantity as well. Both of them look at the same thing, but in a slightly different way. So, both Pache index and Laspe index looks at changes in price and changes in quantity, but the way they are calculated is a little bit different. So they are composite, but they are weighted average now. So this is given in the question, and then I have done some calculations. So original question is, we have quantity in 2010 given in thousands for product PQRST, and then we have price in 2010 given for PQRST, and then quantity in 2012 given, and quantity and price in 2010. If we look at the simple price index, like we saw here, composite price index, we would look at 23 price and 29. Take 29, divide by 23, which becomes 126. But it doesn't, it says that the price has increased. But maybe the price, the thing for which the price is increased, we consume less. Maybe the price, the item for which the price has decreased, maybe we consume that more. So it doesn't give a good picture. That's why we have these Laspe indexes and Pache indexes. So the formula for Pache, now let's look at Laspe price index and Laspe quantity index. Obviously, we are looking at the price of 2010 dividing by the price of 2012 divided by the price of 2010, which would be the simple one. Okay, but it doesn't look at quantity. What we do is we look at the quantities that are consumed. But obviously, you have to do this whole calculation. We look at the price and we multiply by the quantity, which is our P0 and Q0 over here. So basically, you need the price of the base year and the quantity of the base year. The price of the latest year and quantity of the base year. So what Pache does, it uses the same quantity, the base year, same quantity. So I've already done that calculation, but you have to do it individually for each item. Like we have Q0, P0, I've already done. So I have 900 here. So this is price multiplied by quantity for each individual thing. Obviously, if you take the total quantity and multiply total price divide by total quantity, it will not give you exact right figure. So you have to do it individually for each item. So we have Pn and Q0, which is the latest price, divided by the base quantity. We have 1110, and then multiplying by 100, which is 123. So the quantity remains the same, but the price changes. So we have 123. If you look at 29 divided by 23, it was 26. So now this one says that the price has increased, but not as much as 126, because by the quantity that we consume, it doesn't matter that much. So in quantity index, we will look at the quantity change and we will keep the price same. So the base of that one and P0 QN, which is 950. Multiply by 100 becomes 105. If we look at the simple quantity changes, which is 250 quantity and 300 quantity, it gives us 120. But this says quantity has changed only 105, comparing it to price. So quantity index looks at the change in quantity, comparing it to price, and price index looks at the change in price in relation to the change in weighting it with the quantity. So in quantity index, we keep the price same, we only focus on the change in quantity. In price index, we keep the quantity same, we look at only change in price. We do the same thing in Parche, but in last pay we took the base quantity and base price, but in Parche we take the latest quantity and latest price. So we are looking at the change in price in relation to the latest quantity. We are looking at the change in quantity in relation to the latest price. So we need PNQN, latest price, latest quantity, PNQN, which is 1080, and divided by P0QN, which is the top of this part, 950. Multiply by 100, it becomes 113. So it shows lower increase in price, because maybe now we are using different quantities. And then quantity index, we keep the price same but latest. So same top 1080 divided by PNQ0. PNQ0, which is this one. So we have 97. So it shows both Parche's index says both quantity and price has changed lower than what last pay tells us. So which one is better? Parche is superior in that it takes the latest quantity when we are calculating price, and it takes the latest price when we are calculating quantity index. But the negative point is you have to find latest data. If data is available, Parche gives you latest figure. If data is not available, then Parche is simple. If you want to use the benefit of both, the Parche index and the price and the last pay index, what you could do is Once you have found the indexes like I've previously done, take that and multiply by each other. Like I will take the price index. I've already copied it here as well. So this is the same figure I've done previously. So this is the last pay price, and this is the quantity. This is the Pache price and quantity. So if you want to take benefits of both kind of average, what you could do is multiply price with price, which is 123 multiplied by 114 if we round it off, and take square root of that. So 123 multiplied by 114, it gives you 118. So it is kind of average figure, and it has benefits of both of those. Quantity index 105 and 97. Gives you 101. So this is it. Topic wise, next video we will do kit questions.